Right now it's like 1 point for every question. It's supposed to be out of 100. What'll happen is that once you guys all do it, so the percentages will be okay.
I was going to ask you on number 4.
Yeah?
It was talking about radians per minute on a minute hand.
Uh-huh.
Or no, radians per second. Was that 1800? Or 1 over 1800 pi?
I can't answer that. It's a test. I can answer it on Wednesday.
I submitted both mine. Can I ask you after or no?
Yeah, you can ask me after, but I'll answer it on Wednesday.
Yeah, I forgot it hasn't been.
Yeah, it's not done yet. It's not done yet. It's all right. It's okay. So the prep for final that's on WebAssign, that is a quiz that's not droppable. So, and I will tell you it's going to be harder than the final, all right? But it's been open for a while, and I just went in. A couple of you have already started it, but that is a non-droppable quiz, okay? So you've got to get in there and get that quiz done. Okay, that's where that one is. Otherwise, we are doing the rotational motion. I've already got the final made up. I will kind of go over what kinds of problems to study for. Unfortunately, no matter what you do in Physics 1, it is a comprehensive final, all right? I will tell you there will not be any thermodynamics on it, all right? There's no thermodynamics on it at all. But there are a couple of questions related to the stuff we're doing in Chapter 9. But the thermodynamics, all the thermodynamics that you'll have for this semester is in the homework. So that kind of gives you a heads up on studying. The test is Monday of finals week. It's on a day that we don't usually go, and it's at a time we're not usually here. So be careful of that. Margaret will have the tests next Friday, so she'll have them already, and then it'll be the typical thing: Scantron, partial credit written on the test, that normal stuff. All right. I know most of you will want me to email me, what do I have to get on the final to keep my grade? I don't recommend that. It's a psychology problem. Typically, I have seen it over and over again. If you know what you have to make, you miss it. You absolutely miss it, and you fall short. And it's because your brain shuts down when you think you've got the right number of points. And you don't need to do that. You don't want to do that. You don't need to do that. So you don't want to do that. Yeah, it's weird. It's totally weird. I've seen it over and over and over again. Now, if you want, I will put in a 0 for the final on Friday before you guys take the final, so you know what the absolute worst case is. Yeah, that part I will do. That part I will do is the worst case scenario is the 0 on the final, but I don't necessarily do anything else. So other than that, I think we're kind of progressing on, and then I'll hope to see several of you. Not everybody has to take Physics 2, which I think is a bummer. Next spring. That we get in there next spring, because we're getting short. We're getting short. All righty. Was there a question over there in Tonkawa? Okie dokie. So let's see if I can get things working correctly, which is on Friday morning always entertaining. Oh, I got that screen. You guys see the document camera over there? All right. Okay, so we stopped on Wednesday. Oh, and I did get the rest of Chapter 8 lecture posted, and I got Wednesday's lecture posted this morning. So that's all in there. It's all on Blackboard. And so where we had finished on Wednesday is we had just defined pressure as force per unit area, and we talked about the common one that we use is PSI, and that's pounds. This is pounds per square inch, and that's the one that we usually see. This is absolute pressure, okay? All right, this when we say PSI, because a lot of times you'll see something that says PSIG. All right, PSIG stands for pounds per square inch gauge. Okay, it stands for pounds per square inch gauge. And the reason that happens is if I have my car tire, so there's my car tire, and I have my handy dandy little car tire gauge, and usually we do it with these lovely little pressure gauges that has the little stick that comes out. If I do this, that is what we are looking at, is the pounds per square inch gauge pressure. And inside the tire might be, if I've got a low profile tire, I might be at 35 PSI. And that's actually PSIG. It's because this is a differential between what's inside the tire and what's outside. Because both of them have an additional pressure associated with our atmosphere. Okay? So pounds per gauge pressure kind of factors out the difference associated with our atmosphere. Because our atmosphere has pressure associated with it. And so if we think about what's happening on our atmospheres, we've got this little column of air, and all of us are exposed to it all the time. We've got a column of air, and this goes from the surface of the earth up to way past our ionosphere. So if you're doing your good old earth science type stuff, we've got this thick layer of stuff between us and space. And that actually has a force applied to it, because what we've learned is that force is applied through its center of mass, and we have a mass that's sitting there pushing down on us. And that's what we call our pressure due to the atmosphere. Pressure's funny stuff. So let's kind of think through for a second how we measure pressure. So we measure pressure and force per unit area. Our common one is PSI, but we have lots of units of pressure. One we defined on Wednesday is Newton meters squared, which we defined as a Pascal. But we have other units of pressure that are more common. So I'll start asking the question, what unit of pressure are you familiar with? I've already given you two. What other ones are there out there? Because these are, neither one of those are the ones that the weatherman gives you. And we're about to have a change of pressure today. They said we're supposed to have, depending on where you are in the state, they're actually talking golf ball size hail. Yeah, we hear atmospheres. Well, blood pressure is what you're actually measuring on your blood. Okay, but what is the measure? Yeah, millimeters of mercury. Millimeters of mercury. You'll also see centimeters of mercury, which is kind of a weird one. All right, we see centimeters of mercury, but most of the time we see it in millimeters of mercury. And so in atmospheres, we talk about one atmosphere, and one atmosphere in mercury is 760 millimeters of mercury. And if I'm centimeters of mercury, it's like 76. It's just a conversion. There's another one out there, and you usually see the other one when we're measuring a vacuum. You usually see the other one when we're measuring a vacuum. Which is kind of weird because the units are about the same, and it's torr. Okay, and so we usually see it out there when we're measuring. So here comes the next fun question is, how on earth, if we're talking that this is pounds per square inch or force per unit area, that we actually measure pressure in terms of a height? And that's because of how a barometer works. Okay, and I'm about to show you that. So it's terms of how a barometer works. And so I've got my column, except this time it's going to be a column of mercury, so we're actually going to do it. And just so we've got our conversions in there, because there are lots of strange conversions. 1 atmosphere is equal to 14.7 pounds per square inch, which is equal to 1.01 times 10 to the 5th pascals, and this is typically measured at sea level. Because the Earth isn't a nice, smooth, ball-bearing sphere, you know, we got bumpy edges, and so we actually measure that. Do I have any scuba divers? Anybody ever been scuba diving? Okay, nobody's ever been scuba diving. Gee, but you've all heard of something called the bends, right? We've all heard something called the bends, because when I go scuba diving, I have to watch for the change in pressure associated with water. All right, change in pressure associated with water. So I'm going to get to our millimeters of mercury by doing a comparison of our atmosphere to look at how deep if I have a column of water. Okay, I've got a column of water. We want to know the height of my column of water that would equal 1 atmosphere of pressure. Okay, we know in this, we talked about MacGyvering density, right? Density is mass per unit volume. And for water, and we're just going to go ahead and use fresh water, not seawater. And we're going to use fresh water, and I've got 1 times 10 to the 3rd kilograms per meter cubed of water. And we know that 1 atmosphere is equal to 1.01 times 10 to the 5th pascals. So we want to find the height of a column of water that's going to equal 1 atmosphere. So I'm going to do that pressure is equal to force per unit area. Force is going to be the mass times gravity per unit area. And when I do my mass, I'm going to have the volume times density is equal to the mass. So now I've got volume times density times gravity divided by area. Volume is also area times the height. So now I'm going to put area times the height times density times gravity divided by area. Areas cancel. So the areas cancel. So now I have pressure is equal to density, height, gravity. We know the density, we know gravity, we know the pressure that we're looking for. So I can plug that in. I'm going to solve for height. Height is going to equal pressure divided by density times gravity. And that's 1.01 times 10 to the 5th pascals, which is Newton meters squared, divided by the density, which is in 1.00 times 10 to the 3rd kilograms meters cubed, times gravity, which is 9.8 meters per second squared. And we end up with just meters left if you go through the unit analysis, and that works out to be 10.3 meters. And if you're a scuba diver, you happen to remember that about 33 feet is when I'm going to change atmospheres. And if there's about 3 feet to a meter, just doing a rough estimate, 3 feet to a meter, that's about 33 feet. So when you go down 33 feet below the surface of the water, you're going to experience an atmosphere associated with just the water. Which means if you go down 66 feet, you're going to experience 2 atmospheres. When you go down to 93 or 99 feet, almost 100 feet, you experience 3 atmospheres. And one of the things that we know when we increase pressure, because you guys, most of you have learned it in chemistry class, if I have a balloon, so I got a balloon and it's filled with a gas, and I increase the pressure on the balloon, what happens to the volume? So as the pressure goes up, what happens to volume? If the pressure goes up, what happens to my volume? It goes down. So as I increase the pressure, the volume goes down. So if I have a blood vessel and it's got a little bubble of oxygen in it, and I'm at three atmospheres, my blood, I'm going to put that bubble of oxygen is going to be really small. And as I decrease the pressure, what happens to that bubble of oxygen? It's going to increase. And I can rupture a blood vessel. And that's really bad if that happens in your brain. It's really bad on a number of different ways, which is what's called the bends. Is if I increase those or decrease that pressure too fast, my body doesn't have a chance to equilibrate, and I end up with air embolisms, which is one of the reasons we got to worry about it. So now, if we look at that, then because we just derived it. We came back and we showed that pressure was equal to mg over area, and my mass was density, gravity, height. We just kind of derived that, which means now when I measure pressure, I can do millimeters of mercury, or I can do millimeters of ethylene glycol, or I can do millimeters of whatever substance, because I know the density of that substance. So how a barometer works used to be, you had a little tray and an evacuated tube, and this is all filled with mercury, and the tube is filled with mercury. As the pressure increased on my lake here, I would see a change in the height in my tube associated with the change in pressure. And that's why we could actually measure the pressure using millimeters of mercury. So we use pressure a lot. Pressure gives us a variety of different things that happen. If you're in chemistry class, we derived the ideal gas law, right? Pressure is proportional to volume, or the inverse volume. Pressure is proportional to the inverse volume. Because if I have a balloon, just like what we said, if I have a balloon and I increase the pressure, as the pressure increases, the volume decreases. So that's an inverse relationship. We also know that if I have my balloon, and I'm going to keep my balloon in a container here, all right? I'm going to keep my balloon in a container. I'm not going to let its volume increase, but I increase the pressure in there like a bicycle pump. What happens to my bicycle pump as I'm pressuring up the tire? What happens to my bicycle pump as I'm pressuring up the tire? Well, it gets hard to push, but what else happens? What happens if I touch the bicycle pump? What do I see? Doesn't it get hot? Yeah, it gets hot. If it stays in the same volume, I got to do something. And so if I increase the pressure, it gets proportional to temperature, right? Increase in pressure changes the temperature. Decrease in pressure also changes in temperature. And think about it. If I'm emptying out my bicycle tire, or if I've got my finger on the valve of my tire because I've overpressurized my tire and I want to get, let's say I put 38 psi in it and I really wanted it to be 32, and I put my finger on that, what else do I feel? I feel it gets cold, right? It gets totally cold. If I've got a piece of pressurized pipe, or if I've got a pressurized system and I'm releasing pressure, I'm going from high pressure to low pressure, the temperature goes down. And it can be dramatic. In Borger, Texas, on a 110 degree day, you can go out, and if there is a leaking valve where you've got a pressurized pipe and you've got the valve leaking, you'll see ice balls on the valve because you're seeing a change in pressure. That change in pressure is actually cooling down, and it's gotten cold enough that any water that's in the air is actually condensing around the valve, and it can actually freeze. Yeah?
We race cars, and whenever we open a nitrous bottle, it completely frosts the entire deal.
It frosts. Yeah. Well, anybody who's ever released a CO2 fire extinguisher, you get frost like almost instantaneously. So pressure is directly proportional to temperature, which is why we can write the ideal gas law. PV is equal to nRT. So one is, and I always have fun. One is what they call Boyle's Law. One's what they call Bernoulli. Try to keep track of them, right? I can remember Avogadro's because Avogadro's comes with the N. Okay. The reason I can remember it in chemistry class is because I have it in my notes, right? And the only one I would try to remember Avogadro's is because it's related to the number of moles, right? Charles's law is one. Charles's law is temperature, I think. Can't remember. Dalton's law is partial pressure. That one I remember. Partial pressure is Dalton's law. So, I mean, we deal with it, and so pressure, we utilize it a lot. Now, the interesting thing about pressure, and this is where we were talking about the difference between fluids. All right? Fluids can be a gas or a liquid, and that's why we want to be able to look at our system, because we deal with pressure in a lot of different ways, and we utilize its behavior. So anybody's ever gone up and look at their roof, what you find on your roof is you've got 2x4s that are spaced out, right? You got 2x4s that are spaced out. These are usually referred to as purlins. And then you put your sheet, your sheet plywood over the top, right? You put your sheet plywood over the top, and if I've got snow, I've got a force over that entire area, and I'm just distributing that force over a greater area. So even though I've got the purlins, which are taking care of taking the brunt of it, because I've distributed the weight over a bigger area, I'm actually able to handle a heck of a lot of snow on my roof because I've got it distributed. We also use it, so I'm going to use the little Viking sail here. Okay, I've got my Viking sail. And I've got the wind is applying a force. And the bigger my sail, the bigger the area, allows me to get the motion. So we utilize pressure a bunch. And we utilize the change in pressure as well. And we'll get to Bernoulli's principle here in just a little bit about utilizing that change in pressure. One thing I forgot to mention when we're dealing with our gauge pressure and our pressure due to mercury, this is the generalized form. Okay, because we're going to see this again, that depending on where I'm at, if I'm under the water, not only do I have a column of water, I also have whatever the atmospheric pressure is. So what the pressure my little scuba diver is feeling down here with the little flippers is incurred by both the atmospheric pressure and the water pressure. And so that's where we get the generalized form for my change in pressure that we're experiencing, which is why you get gauge pressure, because if I'm measuring what's happening inside the tire versus what's out there, both of them have atmospheric pressure applied, and I'm measuring that differential. Okay. But then we can use this really, really cool. So let's take, and this is the difference between a liquid and a gas. So I have 2 cylinders here. And I can apply a force here, and it's going to give me a resulting force here. Okay? This is why hydraulics work. Somehow I don't think that's spelled right. I think we have to do it this way. It's the French version. There's no O in it. Hydraulics. All right. If I had a gas, gases are compressible because that's how a bicycle pump works. We take our piston and we apply the force, we compress the gas, we see an increase in temperature. The reason we see an increase in temperature is we did work on the gas. All right, we did work on the gas, so that energy had to go somewhere, and that energy ends up going into temperature. So when we have our regular bicycle pump piston, that's what's happening there. I can actually get the gas compressible. But if I have this filled with a liquid, like water or hydraulic fluid, we know by experience that liquids are incompressible. Yeah, they'll compress a little bit, teeny tiny, but not anything to write home about, right? We know we'll get something that happens that it's not going to be very compressible. If I put a piston in water, what's going to happen to us? We're going to see the water escape. If I have a syringe, we see that syringe, if I try to do it, it's going to go out the hole or it's going to come around the edges. You're not going to compress the water, right? The water is not going to be compressed at all. So the force that I apply here comes out on the other side. Sorta. Okay? Sorta. Because we know that's not really what we're doing. So there's a principle out there that says, it's Pascal's principle, that if I have an incompressible fluid, such as water, that the pressure applied here is the same pressure throughout the entire container. Because it's applied all the way around the container. So if I have this force per unit area has got to equal this force per unit area. And this is how when you're on a scale at the truck stop or whatever, the truck rides over here and the person over at the other end reads the scale. It's because I can do that. It's also how your hydraulic system works at the garage, putting the car in. We can actually do this. So this force, so if I have a car over here that's sitting on my hydraulics and it's on an area here, and we're going to say that this is 5 times the area, and we know what the car's got, right? Let's say the car is about 2,000 kilograms. This force applied divided by the area has got to equal the force on the other side divided by its area. So if we say that on this side it's got an area there, we want to know the force that we have to apply in order to raise this particular car. I'm going to have to do it ends up being the force applied divided by 5 is equal to the force that I have to apply on the other side. So to raise this car up here, this 2,000 kilograms times gravity, I can divide my 2,000 kilograms divided by 5 is what I have to put over here, the pressure, the force that I have to apply in order to raise the car up. So we utilize this a lot. We absolutely utilize it a lot. So I think one of your homework problems in this chapter is the syringe problem. You're given the area on this side, right? You're given the area on that side, so it's force per unit area. We know that that's going to be MA, my force is mass times acceleration, divided by the area. And I've got a different area over here, so I can look at the changes. You know, you're trying to look at the change of velocity, you're trying to look at a variety of different things, but that's what's happening on that end. Because you can apply that different force problem. We can also do, and in this chapter, we've got a couple of things that we deal with, looking at how material changes. So from a solid point of view, I can take a sheet of material and put clamps on it. Okay? And if we pull it apart, we know what happens to the material. So if I have a piece of taffy, we know it's going to stretch, right? It's going to stretch out, and it's going to actually what we know happens is we get a little neck, and it kind of stretches out, and ultimately it's going to break. Ultimately, it's going to break. We also know if we have a rubber band, we can pull it and stretch it, and then it goes back to its regular shape. Okay? And so we have materials that if we apply a force, so if we look at a diagram, and I think I have some videos that I've posted in Blackboard that helps get it. If I apply a force, we have what's called an elastic region. So if you think of a rubber band, I can pull it, it gets longer and longer and longer, and as long as I stay in this range and I let go of that force, it goes back to its original shape. But we all know that if I pull that rubber band and I pull it too much, it gets to a point that it deforms. Okay? It actually gets deformation. It deforms. And it won't go back to its original shape. And then we'll end up with another region, and then ultimately it breaks. Okay? Ultimately it breaks. And this, we can look at it as a force per change in length. Okay? We look at it as a force per change in length. Usually when we do these kind of diagrams, we're doing it with respect to one length here. All right? We're measuring this length, this change in length. And we can call this stress. Okay? Stress is defined as, if we're looking at materials, stress is defined as the force per unit area. Strain, when we end up getting in there, is a measure of the deformation. So we get a change in our deformation, we get the measure in the deformation, but one of the things that we know is stress is proportional to strain. Stress is proportional to strain. It's also going to be dependent on the type of material. A rubber band behaves differently than a piece of plastic, which behaves differently than a 2x4, which behaves differently than a piece of concrete. And we get a bunch of those differences there. And so what we end up with, and we look at, as our book refers to it, is that we get stress is proportional to strain. And we define stress as force per unit area. This is for solids. It's some constant that's going to be dependent upon the material. And it's the change in length divided by the original length. If I am doing one dimension, like pulling on a rope, for example, pulling on a rope, I get that constant becomes a Y. I can look it up because indentured servitude is alive and well. It's called graduate school. And there's some poor soul out there measuring these things all the time. And this is what's called the Young's modulus. And that's going to give you the behavior in one direction of a type of material. Now, if I have a carbon fiber, which is really interesting, if I have a carbon fiber, if I'm pulling the carbon fiber along the direction of the fiber, its Young's modulus is really, really high. If I'm pulling across this way, it breaks really, really easy. So it can be even dimension or directional on the material. So depending on the material that you have, you can have it be strong in one direction and very weak in another. If I have an object that's in 2 dimensions, and we know that I can apply the force on one side. So if I have my piece of paper here and I can apply the force on one side, let's see if I can get it to work. I have some handy dandy fun stuff, like sand. But if I hold this end fixed and this end fixed and I push the paper, or I pull the paper, whichever way you do it, we know what happens. We get a deformation. Right? We get a deformation across the paper, and you can actually see the little arrows start to strain here. And that is what we call shear. And we've done that. We've played with shear, right? If we've all seen the car collisions, right? Car collisions get really, really ugly. We've done the crash test dummy thing, right? You do the crash test dummy thing, and you've got your car. So here's the top view of my car. We'll make it a pickup truck because apparently GM doesn't want to make cars anymore, right? So here's the cab of my pickup truck. And if I hit the concrete barrier like this, we know what happens to the car. The car does something like this, right? When you get the front end gets crunched. Or it goes like this, right? And we know, and you can see some really cool things happen, right, in the top of the metal. But we can still write the same equation, and this is the change in x divided by the height, instead of the other, where if I'm looking at it here, this is the h side and this is the x side, and basically what you end up with is something that looks like this, where that's my object now. It gets sheared. Okay, it gets sheared. This is what we refer to as the shear modulus. That's the shear modulus. And let me see if I got them on my blackboard here, because these are fun. These are fun experiments to do. I mean, they're just totally cool experiments to do. Let's see what we got. Blackboard. Versus. Pick one. I thought. Huh? Yeah. Yeah. So again, it's a test. Again, it's a test. All right, let me see. I'll do this. Hang on. Give me a second. Give me a second. I want to go spring semester. We'll do this. Okay, it's about in here somewhere. Actually, we'll do this. Sometimes it's easier to do a Google search. Okay. All right, this is There are a bunch of these shear tests that are out there. This is looking at soil strength. Oh, I want the test. Okay, so there's one piece. Let me see if I can find the concrete one. Because you can see it, and you can actually do them in reinforced. So this is a shear failure in a reinforced piece of concrete beam. See if they're going to get to, I want to get to the test here. There you can see a shear line in concrete beams. That's a shear in a concrete beam. Trusses, does trusses practice? Let's see if I can find my... Never can find things when you want to, right? Oh, let's see if I can do it. Like I said, these are cool tests. So they've got a wooden beam, and they're going to put the force applied in one spot, and you're going to be able to see the deformation and the shear on there when they actually apply the pressure. And they're just freaking fun tests because you break stuff. You're totally breaking stuff. And I'll see if I can find some of the videos that I have. I've got a variety of videos that you can actually watch the shear happen, play with different materials, and so you see the bend that's occurring. You start to see the bend of the piece. And they've got big dials for big scales. I've got several out of the UAE where they've got big, huge pieces of concrete that they go in and they do reinforced or non-reinforced concrete that you'll end up getting, and ultimately you get to a spot with failure. You'll get to a spot with failure. We used to do these on plastics, do polyphenylene sulfide, polypropylene, polymethylpentene, do those kinds there, and it ultimately breaks, and that's a shear. So you get shear forces that come in, and shear is it's just one of those pieces that we end up with. So shear is fun stuff, but the other part is you can do it bulk. Okay, not only can you do it in one dimension, you can do it 2 dimensions, you can do it in 3 dimensions. In 3 dimensions, now it's related to my cube size, whatever my cube size is, except now we talk about the change in pressure with respect to this. And then because we usually are talking about how it changes this direction here, we end up with a change in volume with respect to volume. And this is referred to as the bulk modulus. So we end up with a bulk modulus. So those are some of the problems that you get to do and play with. But then we get to do Archimedes' principle. Archimedes' principle is why things float. Okay? Because one of the fun things is we all know that if I have a surface here, I've got a boat that sits on top of the water, but we know if that boat's made out of iron, we would think it would sink, right? Because if I put all that iron into one part of the object, we know it would sink. I do this with kindergartners. You take an aluminum foil boat. If I get my aluminum foil compressed enough, it's going to sink to the bottom of the glass. But if I have the piece of sheet of aluminum foil out, it floats. So the question is why, right? The question is why. They both have the same force applied to gravity. They both have this part. But we talk about the buoyant force. We end up with the buoyant force. And so Archimedes' principle said, any object completely or partially submerged in a fluid is buoyed up by a force that with the magnitude equal to the weight of the fluid displaced. So the thing about it is how much fluid is displaced. If I don't have enough fluid displaced, my object's going to sink. If I have a bigger fluid displaced, my object's going to float. And the best way to look at this is to look at our iceberg problem. We'll look at the iceberg problem because what we know from an iceberg if I have an iceberg, there's my iceberg, and we know that the water level is right about there because we've all been told that most of the iceberg is below the surface of the water, right? We've all been told. And we know that the density of ice is different than the density of the seawater. So I'm going to give you the density of seawater. Density of seawater is 1,030 kilograms per meter cubed. Turns out the density of ice is 917 kilograms per meter cubed. So we've got two different pieces of density. And so we can ask the question, if the mass of this iceberg, so we know the mass of the iceberg is 100,000 kilograms, we want to know what percent of the iceberg is below the water. Okay, the percent of the iceberg that's below the water. Now, Archimedes' principle says the buoyant force is equal to the amount of the water displaced. So it's going to be related back to the volume of the water displaced and the mass of the volume of water displaced. So the volume of the iceberg is going to equal its mass divided by its density. Okay, it's going to equal its mass divided by the density. So we know its mass, we know its density, so it's 100,000 kilograms. And its density is 917 kilograms per meter cubed. So it's going to have a volume of 109 meters cubed. The buoyant force is equal to the mass of the water displaced. It's going to be related to the mass of the water displaced. So we need to know the volume of the water displaced. And that's going to be its mass. It's going to be the same mass as the iceberg, except now it's divided by, it's 30, sorry. Now it's divided by the mass, or the density of the density of the seawater. And when we do that, it ends up being 97 meters cubed. So the amount of the iceberg that's above the seawater is 109 minus 97. So what we see above the surface of the ocean is 12 cubic meters for this 100,000 kilogram iceberg. And if we do the percentage, we take 12 divided by the 109, and it's about 11%. You can demonstrate this even with something that would sink. So let's take an object, and here's the surface of the water, and it's attached to a scale. The difference, if we measure the weight of the object above the surface of the water, and then we measure the weight of the object below the surface of the water, there's going to be a difference, and the difference is related to the volume of the water displaced, or the weight of the water displaced. So the difference is going to be related to that weight. And that's Archimedes' principle. So even if I have something that sinks all the way to the bottom, it still is going to have a buoyant force applied to it related to the mass of the water, or the weight of the amount of the water that it's displaced. So we get a lot of that fun stuff. And the last one that we have to cover for this chapter is Bernoulli's principle. And I will post, because my pictures aren't all that great when it comes to Bernoulli's principle. But Bernoulli's principle is this. And Bernoulli's principle allows for things like airfoils, because we're looking at the flow of the fluid around an object, or the flow of a fluid through the pipe. As we go through the pipe, the mass that's here has to go through the pipe through there, and we know what happens is we actually see a change in velocity in order to have this occur, because we're not going to bunch up the mass as we get to flow through. And it tells us that the area, so this is area times the velocity, has to equal the area. So this is area 1, velocity 1 has to equal area 2, velocity 2. So I end up getting an increase in velocity as we go through. We can apply the idea of conservation of energy, and we end up getting what we refer to as the general equation for Bernoulli's equation, which is 1/2 the density times velocity squared plus the change in height here. So this happens when I have my pipe go from here to here, or vice versa, because he did that, has to equal some constant. And you can end up with the velocity one out of there, or the other piece that are out there. And that gives us a change in pressure between the two. And that's what is actually going to allow this part to have a raise up, because I'm going to go to a lower pressure and I'm going to raise up and I can actually fly a wing. I will show some videos on Wednesday that help this quite a bit. I'll actually try and get them posted by Monday so that you guys have it for the homework. And one of the things about the buoyant force, just so you can see the equation for buoyant force, buoyant force is equal to the density of the fluid, the volume of the fluid, times gravity. Okay, that's my buoyant force. The density of the fluid times the volume of the fluid times gravity. My Bernoulli's equation works out to be this, and I will post some videos to help make this explain it a little better. And we'll call it a day. Now, Ryan, if you want to talk, you can come to my office later today, because I'll be back over there. But remember, this is a test.
Good day,